Hello everyone, I hope you're doing well. In the previous lecture, we went through Runge-Kutta methods, which is a family of methods for solving ODEs. And we started with the first member of this family, aka Euler's method. So here I'm just going to give you a recap of the previous session and just briefly review the Euler's method. If you remember, the question is to solve the ordinary differential equation of this form. And we know the initial condition, which is, and for time being, we assume that the step size is also given to us, which is equal to the maximum x minus x0 divided by the number of steps. And the Euler's method formula to extrapolate the value of function at the next x was, and if I want to present this graphically, I'll assume that the answer to this ODE is a function like this curve. And I know the value of this function at x0, which is y0. And I want to estimate the value of this function at the next step, which is x1. So the way this method works is to calculate the slope of the tangential line at point x0, which is basically this line, and its slope is equal to dy dx at x0, which is f of x0 and y0. The next step is this method assumes that within this interval from x0 to x1, the function behaves linearly, so it behaves like a line, and it finds the value of function at x1 at the intersection of the tangential line and the vertical line that passes through x1, which is this point. So this is the predicted value for y1. As you can see, clearly there is an error between the predicted value and the true value of y1. In today's lecture, we will analyze the error of Euler's method, but before we start the analysis, I'll have to give you a couple of background information. And for that, let me just change the color and use blue. So the first background is about sources of numerical error. The previous sections we talked about how we calculate the true error and the approximate error, but we didn't explain what are the sources of numerical error. So in here I will just shortly describe the sources of numerical errors, but I'm not gonna go into the detail. If you're interested, you can refer to the chapter 3 of your textbook and read more information about that. The first type of error is called random error, which is due to the computer representation of a number. In fact, computers can store only up to a certain number of significant figures. So when we deal with computers, we have to realize that numbers will be saved, stored, and basically manipulated in the computer only up to a fixed number of significant figures. As a result, irrational numbers and special numbers, for example, pi number, which has infinite number of decimal digits, will not be stored or represented exactly in the computer. So what happens is when we store these numbers in the computer, depending on the precision of the computer or the precision of the software package that we use, only a portion of the significant digits will be retained, and the rest will be either chopped off or rounded. So what happens is, through our numerical calculation, we will lose some accuracy, and that's due to roundoff error. But the next type of error is called truncation error. When we talked about Taylor series expansion, we briefly explained the truncation error, but here to recap, the truncation error is due to the numerical methods and basically the approximations that we use to represent an exact expression. I will shortly give you an example of truncation error in the context of Taylor series expansion. So for now, we know that there are two sources of numerical error. So our second background is about Taylor series expansion. If you remember, we explained that Taylor series expansion can be used to estimate the value of a function in a proximity of a point, for example, x equal to a, if we have the value of function and its derivative at point a. And the formula that we use is so up to here there is nothing new, and we know that Taylor series expansion has infinite number of terms, but technically we have to truncate it at some point. And when we do so, we are basically discarding some terms, and for that we have to introduce an error which is called the truncation error. So this is in line with the second source of error for numerical calculation that I just explained. So the new point that I'm going to make in here is about the order of the truncation error for the Taylor series expansion. And with some mathematical work, we can prove that the truncation error is on the order of x minus a to the power of n plus 1. Now we're going to implement this background knowledge into the Euler's method and analyze its error. This time I'll try to derive the Euler's method formula using an alternative approach, which is based on the Taylor series expansion. So I'll just briefly rewrite the problem description here. So we have an ODE in the form of y prime is f of x and y. And the initial condition is y at x0 is y0. And the step size is h. So if I just rewrite the Taylor series expansion, but this time in the same notation that we use for Euler's method, I will have and we will truncate the Taylor series expansion right after the second term, and we introduce the truncation error in here. If you remember, we call this the first order Taylor polynomial. And based on the concept that I just introduced in here, the truncation error for this case will be on the order of xi plus 1 minus xi to the power of 2. And I just remind you that xi plus 1 minus xi is h. So I can say that the truncation error is on the order of h to the power of 2. Now let's implement this into our graphical representation. So this time let's assume the function is like this. And we have the value of the function at this point. So to estimate the value of the function at x1, we draw the tangential line at x0 and we find the intersection with the vertical line that goes through x1, and this is our predicted value for y1. And this is the true value for y1, and we know the difference is called the truncation error. Now let's try to estimate the value of function at the next point, which is x2. For that, we calculate the slope of the curve at x1, which is the slope of this line, and we know that the calculation of the slope is exact, but because we have to apply it to our predicted value, we will get something like this, and this point will be our estimate of y2. Now if you look at here, the truncation error from step 1 has been propagated to the next step. So if I call this truncation error 1, this is exactly the same as the error from the first step, plus we have a new error, which is the truncation error in the second step. And the sum of these two create what we call it the global truncation error. So in other words, h squared is the order of truncation error for each step of the Euler's method, but the error from each step propagates to the next step and so on and so forth. And sometimes the errors are of the same sign, so they just add up together. Sometimes they could be of different signs, so they may partially cancel out each other. But what happens is at the end of the day, we have two definitions of the truncation error. One of them, we're gonna call it the local truncation error, which is basically what we just calculated here. And we explain that through mathematical work, we can show that it's on the order of h squared. And the other one, which is the sum of all of the truncation errors from the previous step, it's called the global truncation error. And again, through mathematical work, we can show that this is on the order of h. At this point, we can make three important conclusions about the error of Euler's method. First is that the local truncation error, or the truncation error corresponding to the each step of the Euler's method, is on the order of h squared. The global truncation error is on the order of h. And finally, we know that the value of a step size, or h, defines the accuracy of the method. So the smaller the step size, the more accurate our results will be. Next, I will show you some of these concepts through solving an example in Excel. Okay, I created this Excel sheet for the example that we initially started to solve in the previous session. The question asks us to numerically integrate this ODE, or in other words, find y of x. And for this specific question, we can obtain an analytical solution simply by integrating the right-hand side of the equation and using the initial condition, which gives us this expression for the function y. But we are just going to use this for the sake of comparison and to calculate the true error. The question asks us to integrate the ODE in the range of x between 0 to 4 and using a step size of 0.5. We are using the Euler's method, which follows this formula in here and uses the derivative of the function at each specific point to extrapolate the value of the function at the next point. And we know that the derivative of the function is equal to the right hand side of this equation, which is again given in here. I have generated the first two steps of the numerical integration, which give me the value of the function at 0.5 and 1. Now, if I click on this cell, you can see in the formula bar that I have entered the Euler's formula. The predicted value of the function using Euler's method is 5.25, whereas the true value of the function, which is calculated using the analytical solution, is 3.22. This last column is the relative true error, And you can see for the first point, the relative true error is almost 63%. And for the second point, the relative error is even larger, which is 95.8%. So to continue the iterations until I cover the whole range, I will just copy these two lines and just paste them down below. And you can see that I have the predicted value of function and the true value of function at the intervals of 0.5. Now, if I zoom out, here to the right, I plotted the true function, which is this blue curve, and also the predicted value of the function at these intervals using the Euler's method, which are these black dots. Now, getting back to our analysis of the error, we mentioned that by decreasing the step size, we can improve the accuracy of the Euler's method. So if I look at the errors, the maximum error in here is 133%. So I created a cell in here that registers the maximum error among all of these points. What I'll do next is I'll just change the step size to 0.25, which is half of the original step size. And because now it's half of the step size, I have more iteration to cover the same range. So I will just copy these two rows and continue the iterations until I get again the same range, which is from 0 to 4. Now, if you look at the numerical prediction of the function, you can see that this time we have definitely a smaller error. And the maximum error among all of these steps is now 66%, which corresponds to the last step or the last point of integration. And this is just an accident, but we can use it as an opportunity to basically evaluate our analysis of the error. So for that, let me just undo some of the operations that I've done. So I'll just go Control Z. Okay, so we are back to the original step size of 0.5 and the maximum error is 133.3%. And again, you can see that the error corresponds to the last step of integration. And the reason I say that this is an opportunity because the maximum error does not necessarily happen at the last step, but it happened in here. And the good thing is the error of the last step is basically the global error because it includes the local truncation errors of each and every one of these steps. So we are looking at the global truncation error. Now let me just go forward. So by cutting the step size from 0.5 to 0.25, or in other words, by cutting the step size into half, we were able to go from 133 to 66.7. So basically, we were able to cut the global error into half. And this confirms our conclusion about global truncation error for Euler's method, which was on the order of a step size. I think at this point I can stop. Thank you for your time, and I'll see you in the next lecture.